There is a version of the universe that is clean and orderly. In that version, stars form by well-understood rules, planets orbit in predictable paths, galaxies cluster into recognizable structures, and everything that happens can be explained with the right equation applied carefully enough. That version of the universe is real, and it accounts for most of what astronomers observe on any given night. But then, there is the other universe, the one that occasionally sends a signal so bizarre that a scientist scribbles a single word in the margin of a printout and circles it. The one that produces stars behaving in ways no known physics can cleanly account for. Radio rings wider than entire galaxy clusters. Objects passing through our solar system that defy every model built to describe them. And voids so empty they feel less like a natural absence and more like something was deliberately cleared away. The universe, it turns out, is a patient and persistent rule breaker. What makes these anomalies genuinely strange is not just that they are surprising. Astronomy is full of surprises. New telescopes reveal new things, and most of those new things eventually find their place in the existing framework. They are either understood immediately or understood within a few years when better data arrives. The uncertainty around them is not the uncertainty of whether they exist. It is the far more interesting uncertainty of what they are, what created them, and what their existence means for everything we thought we understood about the cosmos. On the evening of August 15th, 1977, a radio telescope called Big Ear was doing what it was designed to do, scanning the sky for signals that might not be natural in origin. Big Ear was part of Ohio State University's program in the search for extraterrestrial intelligence, and on most nights, it returned nothing remarkable. Sheets of data filled with the expected static of the cosmos, background radiation hissing at a level that had become entirely familiar to the team reading the printouts. Then, for 72 seconds, something different arrived. The signal came in at a frequency of approximately 1,420 megahertz, which is significant. That frequency corresponds to the natural emission of neutral hydrogen atoms, the most abundant element in the universe. Because hydrogen radiates at this frequency anywhere in space, and because any sufficiently advanced civilization would understand this, scientists had long argued that 1,420 megahertz was the most logical channel on which to broadcast or listen for an intentional signal. It was sometimes called the cosmic watering hole, the frequency where, by shared understanding of the universe's chemistry, intelligent life might naturally gather to listen. What Big Ear received at 1,420 megahertz that night was not background noise. It was a narrowband signal, one confined to a very tight range of frequencies, which is how deliberately transmitted signals tend to look, as opposed to the broadband noise that most natural sources produce. And it was strong. A physicist named Jerry Eman was reviewing the data printouts days later when he encountered the numbers that described it. Radio signal strength was recorded on a scale where a single letter or digit represented the intensity relative to background. The wow signal peaked at a value of 37, represented in the system as the character sequence 6EQUJ5, numbers and letters climbing and then falling as the signal drifted through the beam. Eamon grabbed a red pen and circled the sequence. In the margin, he wrote one word. Wow. The signal lasted exactly as long as a fixed point in the sky would be expected to remain in Big Ear's beam as the Earth rotated, 72 seconds. That duration was consistent with the signal coming from a specific location in space, rather than from any source nearby. It appeared to originate from somewhere in the direction of the constellation Sagittarius, in a region of sky containing no known radio-loud stars, no known pulsars, no known transmitters of any kind. And then it was gone. Every subsequent search, using Big Ear, using other telescopes, using increasingly sensitive equipment over the following decades, found nothing. The signal was never repeated. The sky where it came from was clean and silent. What makes it difficult to dismiss as a simple fluke is the combination of factors that aligned simultaneously. The frequency match with neutral hydrogen, the narrowband character, the correct duration for a fixed cosmic source, the intensity so far above background, the complete absence of any natural explanation for that particular frequency and that particular structure from that particular patch of sky. Taken individually, each of these could be explained away. Together, they have resisted a satisfying natural explanation for nearly half a century. Various hypotheses have been advanced over the years. A 2017 paper proposed that the signal might have been caused by two comets whose hydrogen clouds happened to pass through Big Ear's beam at that moment, producing an emission at the hydrogen frequency. The comets, designated P/2008Y2 Gibbs and 266/P Christensen, were identified as having been in approximately the right region of the sky. The comet hypothesis was immediately contested by other researchers, who noted that comets had never been observed to produce narrowband radio emission of that intensity, and that the proposed mechanism did not hold up to quantitative scrutiny. The debate has not been resolved. The truth is that the wow signal is genuinely unexplained. It is not explained by comets, not explained by any known natural astrophysical source at that frequency and intensity, and not repeated often enough to be pinned down. Whether it was a transmission from an intelligent civilization, a one-time natural event produced by some mechanism that has never been identified, or a coincidence of factors so unusual that it has simply never recurred, nobody knows. What can be said with complete confidence is that for 72 seconds in August 1977, something sent a signal that one physicist thought was extraordinary enough to mark with a single word, and that the universe has not seen fit to explain it since. Most stars dim when something passes in front of them. That is the principle behind the transit method of exoplanet detection. A planet crossing between its star and the observer blocks a tiny fraction of the star's light, producing a measurable dip. For a Jupiter-sized planet orbiting a Sun-like star, that dip is about 1%. For an Earth-sized planet, it is roughly 0.01%. The dips are small, regular, and predictable. They repeat with the same depth and the same period because planets are solid, round, and reliable. KIC 8462852 does not behave like this. The star sits about 1,470 light-years from Earth in the constellation Cygnus, and it is by all external measures a perfectly ordinary F-type main sequence star. Slightly hotter and larger than the Sun, but nothing unusual. What it does, however, is genuinely without parallel. Its brightness drops in ways that violate every assumption the transit model depends on. The dips are irregular. They do not repeat on any fixed schedule. They are asymmetric. The star dims more steeply on one side of each dip than the other, which is inconsistent with a solid spherical object doing the blocking. And most remarkably, they are deep. Some of the dips recorded by the Kepler Space Telescope during its observation of this region reduced the star's brightness by as much as 22%. Nothing currently orbiting this star in any conventional sense, no planet, no moon, and no binary companion could block that much light. Even a planet the size of Jupiter would only cut output by roughly 1%. The star came to widespread public attention through a citizen science project called Planet Hunters, in which volunteers sorted through Kepler data looking for interesting signals. Several volunteers independently flagged KIC4628852 as requiring a closer look. An astronomer named Tabitha Boyajian led the formal study, and the star was subsequently named after her, Tabby's star, after a public vote, though it also goes by the designation WTF001, an acronym standing for Where's the Flux, in a paper that summarized the bewilderment of everyone who had looked at the data carefully. The dipping behavior is not only strange in its depth and irregularity, it is also strange in that it is accompanied by a long-term secular dimming. Historical photographic plates from over a century ago show that Tabby's star has been fading gradually for at least 100 years, losing several percent of its total brightness over that period, in addition to the irregular short-term drops. No single explanation accounts for both phenomena. The hypotheses that emerged ranged from the conservative to the dramatic. The most famous suggestion, which attracted enormous public attention in 2015, was the idea that the irregular dimming might be consistent with a massive construction project around the star. A hypothetical megastructure built by an advanced civilization, sometimes loosely called a Dyson sphere, designed to capture stellar energy and therefore capable of blocking irregular fractions of light, depending on the geometry of the structure. The scientist who proposed this possibility, Jason Wright of Penn State, was careful to describe it as the least likely of the available options, but it was the one that traveled furthest. More conventional explanations include swarms of comets or other debris in extremely eccentric orbits around the star, clouds of fine dust that are optically thicker in some directions than others, or a disk of material from a relatively recent planetary collision that has not yet settled. The infrared excess that would be expected if large amounts of dust were blocking the star. Dust absorbs visible light and re-emits it as infrared radiation, is present but smaller than the degree of dimming would suggest if dust alone were responsible. The long-term fading is particularly hard to explain with comets or dust, because any debris cloud that could produce a century of gradual dimming would need to be enormous, and its presence would leave traces in other wavelengths that have not been consistently found. As of the mid-2020s, the leading explanation involves circumstellar dust, fine particles distributed in some complex structure that is not a uniform disk, varying in density in ways that produce irregular dimming without requiring exotic physics. But the detailed mechanism remains contested. Nothing in the sky behaves the way Tabby's star does, and the data has now been accumulating for long enough that the strangeness cannot be attributed to a gap in the Kepler record or a temporary instrumental quirk. The star is doing something. The something remains genuinely unidentified. In October 2017, an astronomer named Robert Werrick was reviewing images taken by the Pan-STARRS telescope in Hawaii when he noticed a faint, fast-moving point of light that did not belong to any known solar system object. It was already past its closest approach to the Sun and accelerating away. Further analysis of its trajectory made clear that it had not arrived from anywhere within the solar system. It came from interstellar space. The first object ever confirmed to have traveled through the void between stars and entered our solar neighborhood as a visitor. It was named Oumuamua, a Hawaiian word meaning something like a scout or messenger from the distant past arriving first. The initial observations focused on establishing its origin and orbit, but as data accumulated, something in the numbers became troubling. Objects moving through the solar system after a close approach to the Sun are subject to well-understood forces such as the Sun's gravity, the gravity of the planets, and in the case of comets, an additional push from outgassing. When a comet's volatile surface materials are heated by sunlight and vaporized, the escaping gas acts as a weak thruster, nudging the object off the purely gravitational path. When researchers applied these corrections to Oumuamua's trajectory, they found a residual acceleration that no known force could account for. The object was speeding away from the Sun faster than gravity and any other identified mechanism could explain. For a comet, the explanation would be simple: outgassing. But Oumuamua showed no signs of a coma. The hazy cloud of gas and dust that surrounds an actively outgassing comet. Every telescope that observed it found a clean, star-like point of light with no visible envelope of material. If outgassing was pushing it, the outgassing was happening without producing any detectable coma, which was itself unprecedented. The shape of the object added another layer of strangeness. Because astronomers could not resolve it into a disk, it was too small and too distant. They inferred its shape from the way its brightness varied as it rotated. The brightness fluctuated by a factor of about 10 over the course of each rotation, which implied either a wildly elongated shape, something like a cigar or a pancake, with a length to width ratio of perhaps 6 to 1 or more, or a surface with dramatically different reflectivities across different faces. Neither option was consistent with any asteroid or comet ever observed within the solar system, where even the most elongated known objects have ratios of roughly 2 or 3 to 1 at most. The combination of these features, anomalous acceleration, no outgassing coma, and extreme shape, led to a range of proposed explanations. Some researchers suggested that Oumuamua might be a hydrogen iceberg, composed primarily of solid molecular hydrogen that outgassed invisibly because hydrogen gas cannot be easily detected from Earth. Others proposed it was a shard of a larger body destroyed by tidal forces around a distant star. The astrophysicist Avi Loeb at Harvard published an argument that the non-gravitational acceleration was consistent with the behavior of a thin, lightweight solar sail, a physical structure that accelerates under radiation pressure, something like a sail pushed by wind, but using light instead. Loeb argued that no natural process readily explained all the anomalies simultaneously, and that the solar sail hypothesis should not be dismissed simply because of its implications. The scientific community was largely unconvinced, finding the natural explanations more likely, even if each required some degree of novelty. The debate generated more heat than resolution, partly because Oumuamua was departing as it was being studied, and there was simply no time to launch a follow-up mission before it was gone. Then, in 2019, a second interstellar object was found, 2I/Borisov. Unlike its predecessor, Borisov was a perfectly ordinary comet by every measure. It had a coma, it outgassed in expected proportions. Its trajectory showed the exact acceleration a cometary outgassing model would predict, and its shape appeared entirely conventional. It was simply a comet from another star system, behaving exactly as comets from our own star system behave. The contrast between the two interstellar visitors was stark. Borisov suggested that interstellar comets are probably common and probably normal. Oumuamua, by contrast, remained anomalous. If Oumuamua were a natural object, it was a type of natural object unlike anything in any catalogue, behaving in ways that required at least one ad hoc assumption to explain. The discovery of Borisov made it harder, not easier, to argue that Oumuamua was just an unremarkable interstellar pebble. What Oumuamua was exactly is still unknown. The solar sail hypothesis remains controversial. The hydrogen iceberg model has significant thermodynamic problems. Solid molecular hydrogen is unstable over interstellar travel timescales, under most conditions. The tidally disrupted fragment model requires specific circumstances that may or may not be plausible. The scientific literature continues to accumulate papers proposing and countering each explanation. Meanwhile, the object itself is far beyond the reach of any existing or planned instrument, sailing silently toward the outer edges of the solar system and beyond. But the story did not end when Oumuamua disappeared from instrument range. It generated one of the most public and contentious debates in recent astronomical history, centered on a fundamental question about scientific method. How much evidence is required before exotic explanations? Specifically, explanations that invoke the possible involvement of intelligent non-human technology are admitted to serious consideration. Avi Loeb's public advocacy for the solar sail hypothesis drew fierce criticism from colleagues who felt he was promoting speculation without adequate evidentiary support, and equally fierce defense from others who argued that the rejection was driven more by social norms within the scientific community than by the merits of the evidence. The argument crystallized a genuine methodological tension in astronomy that predates Oumuamua and will outlast it. One productive outcome was institutional. Loeb founded the Galileo Project in 2021, a formal research initiative dedicated to the systematic search for evidence of extraterrestrial technological artifacts in the solar system and on Earth's surface. The project uses arrays of high-resolution cameras, artificial intelligence image classification, and established astronomical methods to catalogue anomalous objects in Earth's atmosphere and solar vicinity. Whether it will eventually find something clearly artificial is an open question. What it has already done is bring a previously informal and stigmatized area of inquiry into the framework of funded, published, peer-reviewed research, a transition with consequences for the field regardless of what the cameras eventually find. The broader legacy of Oumuamua may ultimately be infrastructural. Its discovery was essentially accidental. Pan-STARRS detected it only after it had already passed its closest approach and was already accelerating away. The window for detailed study was a matter of weeks. When the next interstellar object crosses the inner solar system, astronomers intend to be ready with far earlier warning and possibly a rapid response spacecraft capable of intercepting it for close-up study. The European Space Agency's Comet Interceptor mission, approved and under development, is designed precisely for this scenario. A spacecraft waiting at a gravitational equilibrium point, ready to be redirected toward an interstellar visitor within months of its discovery. The specific strangeness of Oumuamua created the scientific and political will to build that infrastructure. The next visitor will be met very differently than the last one. On June 16th, 2018, a transient event appeared in a spiral galaxy about 200 million light-years away in the constellation Hercules. Within a few days, it had reached a peak luminosity 10 to 100 times brighter than any ordinary supernova. Within 2 weeks, it had faded to half that peak. Within a month, it was nearly gone. Supernovae typically take weeks or months to reach peak brightness, and then months more to fade. The light curve, the graph of brightness over time, has a characteristic shape that astronomers have been measuring for decades. This event had a completely different shape. A sudden, violent rise, and an almost equally sudden collapse, as if someone had briefly switched on a star 10 billion times brighter than the sun, and then switched it off again. The automated sky survey that detected it assigned it the designation AT2018COW, which is simply a sequential catalog number. The letters cow appear by coincidence, but the name stuck. It became known informally as the cow. The spectral data showed something else unusual. The explosion was extremely hot and extremely blue from the beginning, with very little of the red-shifted, slower-moving ejecta that supernovae typically produce as their outer layers are thrown outward. The cow's outer material was moving at roughly 10% the speed of light, which is fast but not extraordinary for energetic supernovae. What was extraordinary was what it was not doing. The spectrum showed almost no heavy elements being manufactured in the explosion. A strange absence, since the nucleosynthesis of heavy elements in stellar explosions was supposed to be one of the primary outputs of events like this. Most supernovae become opaque in the first days after explosion, as the expanding shell of ejected material is thick enough to block the view of whatever central engine is driving the event. The cow, by contrast, remained transparent enough for astronomers to peer relatively close to its center, almost from the start, suggesting the amount of ejected material was much smaller than in a typical supernova. That transparency was scientifically valuable because it allowed observations that would normally be impossible. And what those observations suggested was the formation of either a neutron star or a black hole at the center, actively feeding on surrounding material and radiating at enormous intensity. This is sometimes called a central engine, and its presence would help explain both the extreme brightness and the unusual spectral signature. The cow opened a new classification in astronomy. The broader family it belongs to became known as fast blue optical transients, or FBOTs. They are rare enough that only a handful had been catalogued by the mid-2020s, but they appear to include events at the extreme end of stellar death. the collapse of very massive stars into black holes in circumstances that channel energy in ways not seen in conventional supernovae. Or possibly the tidal disruption of a star by a black hole in a configuration that produces unusual radiation. The exact mechanism producing the cow's particular set of features is still being refined. What is clear is that when it appeared, it did not fit into any category that existed before it, and the category created to contain it has since been populated only slowly, with events that share some, but not always, all of its properties. One subsequent detection that has received significant attention is AT2020XND, observed in 2020 and estimated to be about 8.5 billion light-years away. One of the most distant FBOTs yet identified, seen when the universe was roughly half its current age. Its properties closely match the cow's, suggesting that whatever process produces these events is not unique to the local or recent universe. The phenomenon has deep cosmic roots, even if its mechanism remains elusive. 66 elements appear naturally on Earth. Most of them were forged in stars and scattered across the galaxy in supernova explosions before being incorporated into planets, atmospheres, and living things. A smaller number were produced in the intense environments of neutron star mergers. Some of the heaviest, most radioactive elements, the ones near the top of the periodic table, are created in these extremely energetic events and are found in trace quantities in nature, but they decay quickly. Uranium has a half-life of about 4.5 billion years. Plutonium-239 has a half-life of about 24,000 years. The heaviest naturally occurring elements that survive for meaningful geological timescales are the ones with half-lives long enough to persist since their formation. Now consider what it would mean to look at a star's spectrum and find elements with half-lives measured in hours, days, or weeks. That is what Przybylski's star presents. The object, catalogued as HD101065, located about 370 light-years from Earth in the southern constellation Centaurus, was first studied in detail by the Polish-Australian astronomer Antoni Przybylski in the 1960s. Its spectrum was immediately peculiar. Stars are chemically classified by their spectra, which reveal which elements are present in the outer layers and in what proportions. Przybylski's star showed a nearly complete absence of iron, which is one of the most common elements in stellar atmospheres. In its place were spectral lines belonging to rare earth metals, including lanthanides and actinides, at abundances far exceeding anything found in normal stars. This alone placed it in the peculiar A-star category, a class of stars with unusual chemical compositions produced by a physical process called atomic diffusion, in which elements settle and float in the stellar atmosphere based on the competing pressures of gravity pulling them down and radiation pushing them up. Some peculiar A-stars accumulate particular elements at their surfaces at concentrations millions of times higher than would be expected from a typical stellar composition. But Przybylski's star is peculiar even among the peculiar. Analysis of its spectrum over the following decades revealed spectral lines that appeared to belong to elements with atomic numbers above 100. What chemists call the transactinides, or super-heavy elements. These include materials like einsteinium, fermium, mendelevium, and nobelium, created in nuclear reactors and particle accelerators, and exist only in vanishingly small quantities for very short periods of time before they decay. Einsteinium has a longest-lived isotope with a half-life of about 472 days. Fermium's most stable isotope lasts about 100 days. Mendelevium, about 52 days. Nobelium, about 58 minutes for its most stable isotope. If these elements are genuinely present in the spectrum of Przybylski's star, and the spectral identifications, while debated, have been taken seriously by multiple research groups, then the question of how they are there at all becomes urgent. For an element with a half-life of weeks to be detectable in a stellar atmosphere, it would need to be continuously replenished. No known astrophysical process continuously generates these elements in a stellar atmosphere. They are not fusion products of normal stellar burning. They would require either conditions of extraordinary neutron flux that are not associated with the atmosphere of an ordinary star, or some mechanism of production that has not been identified. One hypothesis invokes a very slow neutron capture process happening at the stellar surface, driven by unusual magnetic field configurations that concentrate certain particles. Another more speculative idea is that the star might contain some form of exotic nuclear matter in its interior that undergoes slow decay, emitting particles that trigger a continuous generation of super heavy elements. A third possibility is simply that the spectral identifications are wrong, that the lines attributed to these elements actually belong to more mundane species whose signatures happen to fall at overlapping wavelengths under the conditions present in this star's atmosphere. But the identifications have survived scrutiny for more than 60 years. No convincing alternative assignment for several of the lines has been widely accepted. Przybylski's star sits in the catalogue as one of the few objects in the sky whose published spectral data includes elements that, by the rules of nuclear physics, should not be there. Not because of any lack of observation, but because there is no understood mechanism by which they could survive long enough to be found. The star has attracted attention from an unexpected direction: nuclear physics research into super heavy elements. The periodic table extends beyond the elements found in nature on Earth, into a range of super heavy elements synthesized in laboratories that exist only for fractions of a second before decaying. Some theoretical models of nuclear structure predict the existence of an island of stability, a region of atomic nuclei with particularly favorable proton-to-neutron ratios that might have much longer half-lives than surrounding elements, potentially lasting years, decades, or even longer rather than microseconds. If elements in this island of stability exist and have not yet been synthesized in laboratories, they might, under some theoretical scenarios, be present in environments with exotic neutron sources. Przybylski's star has occasionally been mentioned in this context. If genuinely long-lived super-heavy isotopes exist somewhere on the island of stability, and if some unknown astrophysical process produces and concentrates them in stellar atmospheres, then the anomalous spectral lines might represent an observational window into nuclear physics at a regime that no accelerator on Earth has yet reached. The connection is highly speculative and is not a mainstream explanation, but it illustrates how genuinely unresolved the star's chemistry remains. 60 years of data, and the conversation about its origin is still generating new hypotheses. The universe has a birthday. Based on the rate of cosmic expansion, the temperature and pattern of the cosmic microwave background, and the density of matter and energy, the current best estimate for the age of the universe is approximately 13.8 billion years. That number has been refined over decades and is now precise enough that even accounting for remaining uncertainties, the universe is almost certainly between 13.6 and 14.0 billion years old. Stars which form from gas condensed after the universe itself was already underway cannot be older than the universe that produced them. If a star's measured age exceeds 13.8 billion years, one of two things is true. Either the star's age has been measured incorrectly, or the universe is older than currently believed. HD 140283 is a metal-poor subgiant star located about 200 light-years from Earth in the constellation Libra. Close enough that it can be seen with binoculars under good conditions. It is one of the best studied individual stars in the sky precisely because of its proximity, and its properties have been measured with exceptional precision. It is known to be very old because it is extraordinarily metal poor. It contains almost no elements heavier than helium, which means it formed very early in cosmic history, before multiple generations of stellar deaths had enriched the interstellar medium with heavier elements. The oldest stars are the most metal poor because they formed from gas that had not yet been seeded with the products of stellar nucleosynthesis. The question is exactly how old. When astronomers use well-established stellar physics to model how a star of this mass and composition ages, how it burns through hydrogen on the main sequence, how its structure evolves, how its luminosity changes over time, and then compare that model to HD 140283's current observed state, the answer that emerges is unsettling. Early determinations gave ages well above 14 billion years, and some estimates pushed as high as 16 billion years, with formal error bars that did not comfortably overlap with 13.8 billion. The star was older than the universe was thought to be. The age of a star is not measured directly. It is inferred from a combination of its distance, its luminosity, its composition, and the theoretical models used to predict how stars of a given mass and metallicity evolve. Each of these inputs carries its own uncertainty, and the uncertainties compound when they are combined. In 2013, a team led by Howard Bond at the Space Telescope Science Institute used the Hubble Space Telescope to refine the parallax measurement of HD 140283, its precise distance, with greater accuracy than previously possible. The refined distance pulled the star slightly closer than previously assumed, which made it slightly less luminous than previously thought, which in turn made it slightly younger in the stellar models. The new best estimate came out to around 14.27 billion years, with a formal uncertainty of about 800 million years. That error bar reaches down to just below 13.5 billion, which overlaps barely with the lower range of the universe's estimated age. So the star's age and the universe's age are formally consistent if both are at the boundary of their respective uncertainty ranges. The tension is not technically a contradiction, but it is about as close to a contradiction as astronomy gets without something actually being wrong. And many researchers find the proximity of these numbers uncomfortable rather than reassuring. a star born 13.5 billion years ago would have formed within roughly 300 million years of the Big Bang, extremely early in cosmic history, before most galaxies had fully assembled, in an environment that was still mostly hydrogen and helium. The chemistry of HD 140283 is consistent with that timeline. But the margin is razor thin. Some cosmologists have proposed that if the universe's expansion rate is slightly different from the most commonly used values, there is an ongoing and unresolved debate about the precise value of the Hubble constant, the number that describes how fast the universe is expanding. Then the universe might be somewhat older than 13.8 billion years, which would relieve the tension. Others maintain that refinements in stellar physics models, particularly the treatment of convection and element diffusion inside stars, will eventually push the stellar age estimate down enough to eliminate the conflict entirely. Neither resolution has been definitively achieved. The Methuselah star remains on the edge of the universe's timeline, hinting at either a measurement that needs refining or a cosmology that is not quite as settled as it appears. Galaxies are social. They aggregate into groups, clusters, and superclusters. Gravitational families that stretch across tens of millions to hundreds of millions of light years. The distribution of galaxies across the observable universe is not random, but it is not uniform either. It follows a pattern sometimes called the cosmic web. Filaments of galaxies and dark matter that form vast sheets and chains with enormous voids between them where galaxy density falls sharply. Voids are normal. They are built into the structure of the universe from very early on, when tiny quantum fluctuations in the density of the early cosmos grew over billions of years into the large-scale architecture visible today. But there is a void so large that when it was first measured, the astronomers who found it suspected they had made an error. In 1981, the Harvard-Smithsonian Center for Astrophysics was conducting a survey of galaxy positions, a systematic project to map the three-dimensional distribution of galaxies across a region of sky. Two astronomers, Robert Kirshner and August Umler, were part of a team examining a patch of sky in the direction of the constellation Boötes. What they found was a roughly spherical region centered on a point about 700 million light-years away that contained almost no galaxies. Not fewer galaxies than average, almost none at all. A volume of space spanning approximately 330 million light-years across that held, in the original survey, only a handful of galaxies where thousands would have been expected. The team initially thought something had gone wrong with the survey. They went back and checked. The void was real. The Boötes void, as it became known, is not perfectly empty. Subsequent, deeper surveys over the following decades have identified a few dozen galaxies within it, where a typical region of space that size would contain somewhere in the range of 2,000. That is not a minor underdensity. That is a region that is, by any reasonable measure, profoundly hollow. Some of the galaxies found within it appear to cluster toward its walls rather than its interior, consistent with the idea that the void is still evacuating, still in the process of gravitationally pulling material toward its edges. The question of how it formed has not been satisfyingly answered. In the standard model of cosmic structure formation, voids grow from regions that were slightly underdense at the time of the Big Bang. Dark matter in those regions does not have enough density to collapse inward, and over time it continues to evacuate outward towards surrounding regions that are denser, leaving the void increasingly hollow as the universe expands. This process operates on all scales, producing a hierarchy of voids from small to large. But the Boötes void is at the extreme end of what this process is expected to produce within the observable universe's current age. Cosmological simulations of large-scale structure formation predict that voids on this scale should exist, but only rarely, and the Boötes void is one of the largest identified. When Robert Kirshner reportedly observed that if the Milky Way had been located near the center of the Boötes void, humanity would not have discovered the existence of other galaxies until sometime in the 1960s, because the nearest other galaxies would have been the ones at the void's edge, hundreds of millions of light years distant. The observation captured something real about the scale of emptiness involved. It is a region large enough that the nearest galactic neighbor, from a hypothetical vantage point at its center, would be so remote that even our most powerful mid-20th century telescopes might have failed to reach them. The void raises questions that have not been resolved. Is it the product of ordinary cosmic structure formation taken to its statistical extreme? Or does it represent something that the standard model struggles to generate at the right frequency? Some analyses of cosmological simulations suggest that structures the size of the Boötes void appear in models less frequently than a purely random distribution would predict, which hints that some additional physics might be involved, or that the sample of the observable universe is simply not large enough to tell whether the void is genuinely improbable or just a rare outcome of processes that are well understood. The honest answer is that the current data cannot cleanly distinguish between these possibilities, and the Boötes void therefore remains one of the largest genuinely unexplained structures in the known cosmos. What is particularly striking is how the Boötes void interacts with the other large-scale structures around it. The walls of the void, the sheets of galaxies that define its edges, are themselves unusually rich in galaxy content, as though the material that would have occupied the void has been squeezed outward over billions of years, concentrating at the boundaries. This is broadly consistent with the theoretical picture of void evolution, in which underdense regions become more underdense over time as gravity draws material toward the surrounding overdensities, leaving the interior increasingly empty. But the rate of evacuation implied by the void's current depth is at the upper end of what models predict for a structure of this age. One aspect of the Boötes void that received attention in the 1980s but has largely faded from mainstream discussion is a peculiar claim made by Cornell astronomer Carl Sagan and others, that if an advanced technological civilization existed within the void, it might have had millions of years of head start in settling the void's interior, which the nearly empty space would make an ideal environment for expansion. This framing was intended as a playful exercise in the Fermi paradox, the question of why, given the apparent age and size of the galaxy, we see no evidence of technological civilizations beyond our own. The Boötes void was proposed, half seriously, as a region where sufficiently advanced civilization might have deliberately cleared out the matter, though this scenario was never scientifically advocated by anyone in the mainstream. The more prosaic explanation, that the void is simply the outcome of standard large-scale structure formation at a statistically improbable extreme, remains the consensus. But the void's sheer emptiness has a quality that makes even sober observers pause before dismissing the thought entirely. About 380,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before this moment, the universe was a plasma so dense that light could not travel through it. Photons were constantly scattered in every direction by the sea of free electrons. When neutralization happened, light was suddenly free to travel. The photons that were released at that moment have been traveling ever since, stretched by the expansion of the universe into microwave wavelengths. And they bathe the entire sky from every direction today as a faint, nearly uniform glow at a temperature of about 2.7 degrees above absolute zero. This is the cosmic microwave background, a photograph of the universe as it was nearly 14 billion years ago, preserved in the wavelengths of ancient light. It is nearly uniform, but not perfectly so. There are tiny fluctuations in temperature across the sky, regions that are fractionally warmer or cooler than the average, at a level of roughly 1 part in 100,000. These fluctuations were the seeds of all the structure in the universe. The slight overdensities that eventually grew under gravity into galaxies, clusters, and filaments. The pattern of these fluctuations has been mapped with extraordinary precision, first by the WMAP satellite, and then by the Planck satellite. The map matches the predictions of the standard cosmological model with impressive accuracy across most of the sky. There is one region that does not cooperate. In the southern sky, in the direction of the constellation Eridanus, there is a patch of the CMB that is substantially colder than anything expected from the standard model. A region spanning nearly 10 degrees across the sky, where the temperature of the background radiation is measurably lower than the surrounding area. This is called the CMB cold spot. It was identified in WMAP data in 2004 and confirmed with higher precision by Planck. The cold spot is about 70 microkelvin colder than the average background temperature, and it is significantly larger than the typical temperature fluctuations that the standard model predicts. The statistical significance of the cold spot has been debated. Some analyses suggest it is a genuine anomaly, a feature that would occur by chance in only a few % of universes with the same parameters as ours. Others argue that when you search a whole sky map for unusually cold or hot regions, finding one is expected by probability even without invoking new physics, and that the cold spot may simply be the largest example of an ordinary random fluctuation. The debate over its statistical significance has continued since its discovery, and it has not been resolved to everyone's satisfaction. What has been proposed is a range of physical explanations for the cold spot's existence. One that attracted considerable attention is the supervoid hypothesis. A large underdense region of space, a void, in the line of sight between us and the CMB can cool CMB photons as they pass through it, via a mechanism called the integrated Sachs-Wolf effect. As photons enter a large gravitational potential well, a void, paradoxically, creates a kind of negative potential. They gain energy. But in an accelerating universe dominated by dark energy, The void itself changes shape while the photons are traversing it, and the photons do not recover all the energy they gained. They emerge slightly cooler than they entered. A large enough supervoid in the right direction could therefore produce a cold spot in the CMB. In 2015, a team led by Istvan Sapudi at the University of Hawaii reported the identification of a supervoid in the direction of the cold spot, located about 3 billion light-years away and spanning about 1.8 billion light-years. It was described as the largest known void at the time. However, subsequent analyses suggested that even this supervoid, while real, was not quite large enough or deep enough to fully account for the observed temperature deficit in the CMB. The supervoid can explain some of the cold spot, but probably not all of it. This left room for more exotic explanations. The one that has captured the most popular imagination, though it sits at the very edge of current scientific respectability, is the parallel universe hypothesis. In certain models of cosmic inflation, the very early universe underwent a period of extraordinarily rapid expansion that may have produced multiple separate bubble universes. If one of these bubble universes existed adjacent to our own and had physically different properties, a different vacuum energy, a different effective temperature, its gravitational or physical influence on our bubble at the moment of their interaction could have left an imprint in the CMB. The cold spot on this reading is the scar of a collision between our universe and a neighboring one. The hypothesis is taken seriously enough to appear in peer-reviewed papers, and dismissed seriously enough that most cosmologists regard it as a last resort rather than a leading explanation. It cannot currently be confirmed or ruled out. The CMB cold spot therefore exists in an uncomfortable middle position, too anomalous to be comfortably ignored, too ambiguous to demand extraordinary explanations, and too persistent to be waved away as a statistical artifact. It has been in the data for more than 2 decades. It remains in the data today. The radio sky looks very different from the optical sky. Stars, which are brilliant invisible light, are mostly faint or invisible in radio wavelengths. What the radio sky shows instead are supernovae remnants, pulsars, jets from active galactic nuclei, the faint warm glow of hydrogen gas clouds, and backgrounds of distant bright radio sources that were more common in the young universe. Radio astronomy has its own catalogue of objects and its own vocabulary, built up over 70 years of systematic observation. In that catalogue, there was no category for what turned up in data from the Australian Square Kilometre Array Pathfinder, a new generation radio telescope that began science operations around 2019. In 2020, a team led by Australian astronomer Anna Kapinska, and described in a paper by Ray Norris and colleagues, announced the discovery of an entirely new class of radio object, which they named Odd Radio Circles, or ORCs. The first 4 were found in archival ASCAP data. They look like what they sound like, nearly perfect circles of radio emission, with a brighter ring at the edge and a dimmer or empty interior, spanning enormous angular sizes on the sky. They are not the rings of supernova remnants, which have been catalogued exhaustively and look different. They are not planetary nebulae, which are far smaller and associated with known dying stars. They are not radio lobes from active galactic nuclei, which have a different morphology and are typically associated with a visible galaxy between or beside the lobes. ORCs are something else. The scale of these objects is the first thing that demands attention. The handful confirmed as of the mid-2020s are estimated to span distances from roughly 1 million to several million light years, larger than many galaxies, and comparable in some cases to the distances between neighboring galaxies in a cluster. Several of the confirmed ORCs appear to have a galaxy at or near their centers, suggesting the galaxy is either the source of the ring or, at the very least, physically associated with it. In at least one case, the central galaxy appears to have recently undergone a major galactic merger. The leading hypothesis as of the mid-2020s is that ORCs represent the expanding shockwave from some energetic event at the center of the associated galaxy, possibly the merger of two supermassive black holes, which would have released an enormous burst of gravitational radiation and electromagnetic energy at the moment of coalescence. As this energy expands outward over millions of years, it would sweep up surrounding gas and create a roughly spherical shell that, viewed from the outside and in projection, would appear as a ring. The near-perfect circularity of most ORCs fits this idea. A spherical expanding shell would naturally produce a circular projection. The presence of central galaxies at redshifts consistent with the ORCs adds further support. But the hypothesis is far from confirmed. There are features of the ORCs that are difficult to explain with the simple merger explosion model. The sharpness of the rings in some objects, the variation in properties between different ORCs, and the puzzle of why similar events in similar galaxies do not seem to produce ORCs with any regularity. If every pair of merging supermassive black holes created a detectable ORC, the radio sky should be full of them, and it is not. All suggest that either the formation mechanism requires very specific conditions, or the explanation is something else entirely. Only a handful of ORCs had been confirmed by the mid-2020s, which itself tells an important story. They are either genuinely rare, or they are faint enough that only the most sensitive modern radio instruments can detect them, or they fade relatively quickly on cosmic timescales, and we're catching only a small fraction of the total population. The new generation of wide-field radio surveys, including the Square Kilometre Array itself, which began construction in the early 2020s, is expected to find significantly more ORCs once it reaches full sensitivity. Whether that expanded catalogue will settle the question of their origin, or reveal further variations that complicate the current models, is one of the more interesting open questions in observational radio astronomy. Modern cosmology is built on an assumption so foundational that it is sometimes called the cosmological principle. The idea that the universe on sufficiently large scales looks the same in all directions and from all locations. Individual galaxies, clusters, and even superclusters can be distributed unevenly, but above some scale, generally taken to be around 1 billion light years, the universe should smooth out into rough homogeneity. The lumpy structure of the cosmic web, the filaments and voids, should average out at large enough scales to produce a universe that is the same everywhere. This principle is not just a philosophical preference. It is built into the mathematical framework of the standard cosmological model, and the model fits an enormous range of observations with extraordinary precision. But in order for the model to be correct, there should not be coherent structures in the universe that span billions of light years. Large-scale structures of that magnitude would require density fluctuations at a scale where the cosmological principle predicts smoothness. Finding one would be unusual. Finding two at similar distances and in overlapping regions of sky would be something considerably harder to dismiss. In 2021, Alexia Lopez, a PhD student at the University of Central Lancashire, announced the discovery of what she called the Giant Arc, a structure spanning approximately 3.3 billion light-years, visible in the positions of quasars and other distant objects at a redshift of around 0.8, corresponding to a look-back time of about 7 billion years. The Giant Arc is not a physical arc in the conventional sense. It is a coherent alignment of galaxies and quasar systems in a crescent-shaped pattern when mapped in 3 dimensions. Its scale places it well beyond the theoretical limit above which the cosmological principle should apply, meaning it should not exist as a coherent structure if the standard model is entirely correct. The community response was significant but not uniform. Some cosmologists argued that the feature might be a chance alignment, a statistical accident in which the positions of galaxies at a particular distance appeared structured due to the way the survey sampled them. Others took the measurement seriously and explored its implications for the standard model. The debate was ongoing when, in 2024, Lopez announced a second discovery, the Big Ring. This is a roughly circular arrangement of galaxies and quasars, spanning approximately 1.3 billion light-years, located at a similar redshift to the Giant Arc, suggesting both structures exist at roughly the same distance and in overlapping regions of sky. The geometric relationship between a 3.3 billion light-year arc and a 1.3 billion light-year ring at the same cosmic distance in adjacent areas of the sky was not explained by any existing physical model. Neither structure matches the expected signatures of baryon acoustic oscillations. The regular spacing of the galaxy clustering produced by sound waves in the early universe, which does produce large-scale structure, but at a specific and well-understood scale of about 500 million light-years, far smaller than either the Giant Arc or the Big Ring. The two structures are also not aligned in a way consistent with the known filamentary structure of the cosmic web. The implications, if the structures are confirmed as genuine coherent features rather than statistical artifacts, are significant. A universe that contains coherent structures on the scale of 3 billion light-years is a universe in which the cosmological principle breaks down at the scale where it is supposed to hold. The standard model would need modification, either in its description of how large-scale structure forms, or in the inflation models that set the initial conditions, or in both. The debate around these structures continued through the mid-2020s, with proponents and critics producing competing statistical analyses of the same underlying data. The structures have not been proven to be artifacts, and they have not been proven to require new physics. They are, as of now, genuinely open questions about the largest scales the universe has revealed. Fast radio bursts are among the most energetic events in the observable universe, per unit time. In the span of a millisecond or less, a single fast radio burst releases as much energy in radio waves as the sun emits in 3 days. They arrive from distant galaxies, appear to come from compact objects, and leave no obvious afterglow. The first one was discovered in 2007 in archival data from the Parkes Radio Telescope in Australia by astronomer Duncan Lorimer and colleagues, hence the general designation Lorimer burst for the first confirmed example. Since then, hundreds have been catalogued, most of them one-time events, and their origin was one of the deepest mysteries in observational astrophysics for more than a decade. The mystery has not been fully solved, but it was substantially illuminated on April 28, 2020. On that day, a magnetar in our own galaxy, SGR 193 5+2 154, located about 30,000 light-years away in the constellation Vulpecula, produced a burst of X-rays and gamma rays, which was detected by multiple high-energy observatories. Simultaneously, the Chime Radio Telescope in Canada detected a burst of radio waves from the same object, at the same moment, of an intensity and character consistent with the cosmological fast radio bursts seen from other galaxies. If SGR 1935 +2 154 had been placed at extragalactic distances, hundreds of millions of light-years rather than thousands, the radio burst would have looked exactly like the fast radio bursts that had been puzzling astronomers since 2007. Magnetars are neutron stars with extraordinarily powerful magnetic fields. Among the strongest magnetic fields known to exist anywhere in the universe, reaching surface field strengths of 10 to the 15th Gauss or more, roughly 1,000 trillion times the strength of Earth's own magnetic field. These extreme fields can generate enormous stresses in the neutron star's solid crust, causing starquakes, which are sudden, violent rearrangements of the crust material, and these starquakes release energy in cascading bursts of radiation across multiple wavelengths. The 2020 event from SGR 1935 +2 154 showed for the first time that magnetar starquakes are capable of producing radio bursts at the energies seen in cosmological fast radio bursts. This single detection simultaneously provided the most compelling explanation for the majority of fast radio bursts and linked two previously separate mysteries: the origin of fast radio bursts and the physics of extreme neutron stars, into a single framework. But it left open questions. Not all fast radio bursts are the same. Some repeat. Some appear to come from locations within their host galaxies that are inconsistent with where most magnetars would be expected to live. Some have spectra and timing properties that differ from the SGR 1935 +2 154 event. The magnetar model is now the consensus leading explanation, but the diversity of fast radio bursts suggests either that magnetars produce a wider range of events than the single Milky Way detection implied, or that there are additional source types that have not yet been identified. The catalogue maintained by the Chime telescope, which has detected hundreds of fast radio bursts, including several repeating sources, continues to grow. The more examples that accumulate, the more variation becomes visible, and the more the story complicates itself in the way that all good scientific questions tend to do. Every map has its blank spots, regions that instruments cannot reach, wavelengths that conventional telescopes cannot see, directions that are systematically excluded by design. The center of the Milky Way is one of the most studied and simultaneously most obscured regions of the sky. Vast clouds of dust block optical light entirely, making it invisible to conventional telescopes, but accessible to infrared and radio instruments. It is an intensely active region, containing the supermassive black hole at the galaxy's center. Dense star clusters, giant molecular clouds, and magnetic fields of unusual strength. For all the years that astronomers had been studying the center of the galaxy, they had never noticed what was revealed by the Fermi Gamma Ray Space Telescope in 2010. The Fermi telescope, launched in 2008, was designed to detect high-energy gamma rays from across the sky. In data accumulated over the first 2 years of operations, a team led by Meng Su and Douglas Finkbeiner at Harvard identified 2 enormous lobes of gamma ray emission, extending above and below the plane of the Milky Way from the galactic center. Each lobe stretches approximately 25,000 light-years in the direction perpendicular to the galactic disk, one reaching up toward the north galactic pole, one reaching down toward the south. They are not small features. Together, the 2 structures span 50,000 light-years, which is roughly half the diameter of the entire Milky Way disk. The edges of the lobes are unusually sharp for something this large. Most large-scale astrophysical structures have fuzzy, gradual boundaries as the material producing the emission thins out and blends into the surrounding medium. The Fermi bubbles have hard edges that are visible in the gamma-ray maps with a clarity that suggests the boundaries represent a real physical transition. A shock front where expanding material meets surrounding gas, rather than a gradual thinning. Later observations in microwave and X-ray wavelengths confirmed the structures and added further detail about their physical properties. The origin of these structures is not agreed upon. Several hypotheses have been advanced, and more than a decade of further observation has not clearly eliminated any of the leading candidates. The first is an outflow driven by the supermassive black hole at the galactic center, Sagittarius A star, which may have gone through a period of much more intense activity in the relatively recent past, a few million years ago, during which it fed rapidly on surrounding material and launched powerful jets of energy perpendicular to the galactic disk. As those jets propagated outward, they would have inflated the bubbles now visible to Fermi. The sharpness of the edges fits reasonably well with a jet-driven model, as does the symmetry above and below the plane. The second hypothesis invokes not a jet from the black hole, but a burst of intense star formation near the galactic center. When stars form rapidly in a dense region, the collective energy output from supernova explosions, stellar winds, and radiation pressure can drive a large-scale outflow of gas, a galactic superwind. Several nearby galaxies, including the well-known starburst galaxy M82, show spectacular examples of this phenomenon. A starburst near the galactic center a few million years ago could have inflated structures similar to the Fermi bubbles. The challenge with this model is that there is no clear evidence for the kind of intense recent starburst that would be required, though the observational constraints on star formation activity near the galactic center a few million years ago are not tight. A third, more speculative possibility involves dark matter. Some theories predict that dark matter particles can annihilate each other when they meet, releasing energy in the form of gamma rays. The galactic center, which is expected to have a very high density of dark matter, would be the most likely place for this annihilation to produce observable gamma ray emission. The Fermi bubbles are energetically consistent with some dark matter annihilation models, but the spatial morphology and spectral properties do not cleanly match the predictions well enough to make this a compelling explanation on its own. Most researchers regard it as a distant third option rather than a primary hypothesis. What makes the Fermi bubbles genuinely strange is not just that they are large, but that they existed for the entire period of modern astronomy without being noticed. They are not hidden by dust, which blocks optical light from the galactic center, but not gamma rays. They are simply so large and so diffuse in gamma rays that they blended into the background of Fermi's maps until Meng Su applied careful subtraction techniques to isolate them. The structures had been there, producing gamma rays for millions of years. It took a space telescope operating in a wavelength range that had never before been imaged with sufficient sensitivity to reveal them. The question of what inflated them remains genuinely open. For a century after Einstein published the general theory of relativity in 1915, the existence of gravitational waves was accepted on theoretical grounds, but never confirmed by direct measurement. Relativity predicts that any accelerating mass should radiate gravitational waves, ripples in the fabric of space-time that propagate outward at the speed of light. For most sources, these waves are so extraordinarily weak that detecting them was considered essentially impossible. Rotating binary pulsars provided indirect evidence. The orbital decay of a pair of neutron stars orbiting each other matched the rate at which energy should be lost to gravitational wave emission according to general relativity, and the match was precise enough to earn a Nobel Prize in Physics in 1993. But nobody had ever directly felt space-time move. On September 14th, 2015, the two detectors of the Laser Interferometer Gravitational Wave Observatory, LIGO, registered a signal simultaneously, separated by a 7-millisecond arrival time consistent with the speed of light traveling between their two locations in Louisiana and Washington state. The signal lasted about 0.2 seconds, and looked exactly like the chirp predicted by general relativity for the merger of two black holes. The analysis identified the source as two black holes, one of about 36 solar masses, and one of about 29 solar masses, spiraling toward each other at an enormous fraction of the speed of light, and colliding approximately 1.3 billion light years away. In the final fraction of a second before merger, the power output of the collision exceeded the combined luminous power of all the stars in the observable universe. The entire event, billions of years of inspiral, and a final collision of unimaginable violence, produced a distortion in the fabric of space-time that, by the time it reached Earth, amounted to a displacement of the LIGO detector mirrors by less than 1,000th the diameter of a proton. The instruments that detected it are the most sensitive measuring devices ever built by human civilization. The detection of GW150914, named for the date it was observed, confirmed gravitational waves directly for the first time and opened an entirely new branch of astronomy. Within a few years, LIGO and its partner detector Virgo had recorded dozens of confirmed events: black hole mergers, neutron star mergers, and, in one particularly remarkable case, a neutron star merger that was observed simultaneously in gravitational waves and across the full electromagnetic spectrum from radio to gamma rays. The first ever multi-messenger detection of a single event. That event, GW170817, confirmed that neutron star mergers produce kilonovae, identified as a primary source of heavy elements including gold and platinum, and measured the speed of gravitational waves to be equal to the speed of light with extraordinary precision. But what makes gravitational wave astronomy strange is what the catalogue of events has revealed about the universe's black hole population. Several mergers have involved black holes in the so-called intermediate mass gap, a range of masses between about 60 and 150 solar masses, where theoretical models had predicted that stellar evolution should not easily produce black holes, because stars in this mass range are expected to die in a particular type of explosion that disrupts rather than compacts the star's core. GW190521 involved the merger of two black holes of approximately 85 and 66 solar masses, themselves already in the gap, to produce a remnant of around 142 solar masses, the first direct observational evidence for an intermediate mass black hole formed by merger. The existence of black holes in and around the mass gap challenges stellar evolution models that had been considered well understood. The gravitational wave sky is now a permanent feature of modern astronomy. Networks of detectors continue operating and being upgraded. The anomalies in the catalogue accumulate. The universe's black hole population is stranger and more varied than the theoretical framework built before GW150914 was prepared to accommodate. Subsequent observations have added additional surprises. GW190814 was a merger involving one object of about 23 solar masses and another of about 2.6 solar masses. The smaller object falling precisely in a range that could be either the heaviest known neutron star or the lightest known black hole, depending on how you define the boundary. No other object had previously been identified with confidence in this mass range. Whether it was an extraordinary neutron star, spinning rapidly enough to support its mass against collapse, or a black hole lighter than any previously measured, the detection revealed that the mass distribution of compact objects in the universe is not as cleanly separated into two populations as previously believed. The multi-messenger era opened by GW170817, the neutron star merger seen simultaneously in gravitational waves and light, has also produced an unexpected measurement problem. The same event allowed an independent estimate of the Hubble constant, the number describing how fast the universe is expanding, using the gravitational wave signal as a standard siren, a source whose intrinsic brightness can be calculated from physics rather than assumed from an astronomical calibration chain. The gravitational wave measurement gave a Hubble constant somewhat between the two main competing measurements obtained by other methods, which are currently in significant tension with each other. One derived from the cosmic microwave background, and one derived from supernovae in the local universe. More events will improve the precision of the gravitational wave measurement, and it may eventually serve as the independent arbiter that resolves this tension, or deepen the mystery if it splits the difference in an unsatisfying way. A teaspoon of neutron star material would weigh approximately 1 billion metric tons on Earth's surface, This figure is reproduced so frequently in popular science writing that it risks becoming abstract, a number stripped of its meaning by repetition. But it points to something genuinely remarkable about the state of matter inside a neutron star. Matter so dense that the normal rules describing how atoms and subatomic particles behave break down entirely, and physicists are not entirely sure what replaces them. Neutron stars are the remnants of massive stars that have undergone supernova explosions. The outer layers of the star are blasted away in the explosion. The core, which was already held up by the pressure of nuclear fusion, loses that support when fusion ceases and collapses under gravity to a density greater than atomic nuclei. The result is a sphere roughly 12 to 15 kilometers across, smaller than many major cities, containing between 1.5 and 2 times the mass of the Sun. At this density, electrons are forced into protons to form neutrons, and the entire core becomes a kind of enormously magnified atomic nucleus. The outer layers of a neutron star are now reasonably well understood. There is a thin atmosphere, a crust composed of nuclei and electrons arranged in crystalline structures that become increasingly exotic at greater depths, and deeper zones where the nuclear material begins to behave in unfamiliar ways. Below the crust, the density rises further, and the neutrons become free of individual nuclei, forming a fluid of strange matter that does not exist in this form anywhere else in the universe. This neutron fluid likely behaves as a superfluid, a state of matter in which quantum effects produce zero viscosity, meaning the fluid flows without any friction whatsoever. Below that, at the very core of the most massive neutron stars, the density may rise high enough that individual neutrons begin to dissolve into their constituent quarks. Quarks are the fundamental particles that make up protons and neutrons, normally confined in triplets within those particles under ordinary conditions. Under extreme enough pressure, it may become energetically favorable for quarks to exist not in groups of 3, but in a free sea of quark-gluon plasma, the same state of matter that briefly existed in the first microseconds after the Big Bang. If the cores of massive neutron stars contain stable quark matter, they would represent the only macroscopic samples of that primordial state anywhere in the present universe. Whether this happens, whether any neutron star's core reaches quark matter, is genuinely unknown. The problem is that neutron star interiors cannot be directly observed. What can be measured from outside is the star's mass, its radius, and in some cases the way its moment of inertia changes during glitches. Sudden speed-ups in the rotation of pulsars that appear to be driven by the superfluid interior briefly coupling to the crust. Theoretical models of nuclear matter at extreme densities make different predictions for what the radius of a neutron star of a given mass should be. And the gravitational wave observations of neutron star mergers are beginning to provide measurements sensitive enough to constrain these models. The NICER instrument on the International Space Station, designed to time the X-ray emission from pulsars with high precision, has provided some of the best constraints yet on neutron star radii. The picture that is emerging is consistent with a relatively soft equation of state, meaning the matter does not resist compression as strongly as some models predicted, which leaves room for exotic phases of matter at the core without definitively requiring them. The question of what the deepest interior of a neutron star contains may be one of the most fundamental in physics. It touches on the behavior of matter at the extreme edge of what quantum chromodynamics, the theory describing quarks and gluons, can predict, and in a regime that cannot be recreated by any particle accelerator ever built or currently planned. The connection between neutron star physics and gravitational wave astronomy added a dimension to this problem that did not exist before 2017, when two neutron stars merge, an event now detectable in gravitational waves. The tidal distortion each star produces on the other during the inspiral phase encodes information about how stiff or compressible the stellar material is. A stiffer equation of state produces a more tidally distorted star, which produces a slightly different gravitational wave signature. The GW170817 neutron star merger, detected by LIGO and Virgo in 2017, provided the first direct gravitational wave constraint on the neutron star equation of state, ruling out some of the most extreme theoretical models. Future detections and the upgraded detectors designed to be sensitive to a much larger volume of the universe will progressively narrow the range of viable models. There is also the question of what happens at the moment of merger. When two neutron stars collide, they may form a more massive neutron star that then collapses into a black hole, or they may form a black hole immediately, depending on the combined mass and the properties of the matter. The few milliseconds between merger and collapse, if there is a brief, supramassive neutron star intermediate state, could produce gravitational waves at very high frequencies that carry information about the densest matter in the universe. No existing detector can reach those frequencies with sufficient sensitivity. Proposed next-generation instruments, including the Einstein Telescope and Cosmic Explorer, are designed to open that window. Until they do, the interior of the neutron star remains the most densely packed mystery in observational astrophysics. Right there, in every pulsar's ticking, present in every gravitational wave from a binary merger, and still fundamentally opaque. The New Horizons spacecraft, after its famous flyby of Pluto in July 2015, continued outward into the Kuiper Belt, the broad, cold region of the solar system beyond Neptune, where billions of small icy objects orbit in relative isolation. Mission scientists selected a follow-up target using data from the Hubble Space Telescope, a faint, distant object that had been given the provisional designation 2014 MU69. On January 1st, 2019, New Horizons flew past this object at a distance of about 3,500 kilometers, providing the first close-up images. Nothing in planetary science had prepared researchers for what the images showed. 2014 MU69, subsequently given the official name Arakoth, a word from the Powhatan/Algonquian language meaning sky, was not a single object. It was two objects fused gently together, forming a shape that mission scientists described as a contact binary. One lobe, the larger, was named Wenu. The smaller was named Weo. Together they resembled, as the team noted with some amusement, a snowman, or perhaps a flattened peanut. But it was the nature of their fusion that made Arakoth scientifically extraordinary. Contact binaries are not unusual in the solar system. but previous contact binaries were presumed to have formed through collisions. Two objects smashing into each other at high velocity and sticking together in the aftermath. Such a collision would be violent, and the evidence of that violence would be preserved in fractures, deformation, and the scattered debris of impact. Arakoth showed none of this. Its two lobes are smooth, gently rounded, and connected at a narrow neck that shows no sign of the cratering, cracking, or disruption that a high-speed collision would produce. Instead, the shape and contact zone are consistent with what is called a gentle merger, the two lobes gradually spiraling toward each other over a very long period, drawn together by mutual gravity and tidal forces, until they settled softly into contact. This means Arakoth formed from a binary pair, two small objects orbiting a common center of mass in the same collapsing pocket of the primordial solar nebula. Over millions of years, energy was gradually removed from their orbit by a process called Kozai-Lidov oscillations, driven by the gravitational influence of the distant sun, until their orbit shrank enough that they touched. The entire process was slow, gentle, and local, a formation story so quiet that the resulting object retained almost no evidence of violence. Arakoth is believed to be one of the most pristine objects ever studied by spacecraft. It has been sitting in the cold outer solar system for approximately 4.5 billion years, exposed to so little heat and radiation that its surface chemistry has barely evolved since the era of solar system formation. Its reddish coloration comes from complex organic molecules, tholins, produced by cosmic rays acting on nitrogen, ice, and methane surfaces over billions of years. But the underlying structure is thought to represent conditions from the earliest stages of planetary formation. Studying Arakoth is, in a real sense, studying a record of how the solar system assembled itself, one that has not been overwritten by the subsequent 4.5 billion years of geological and collision history. The contact binary formation story, confirmed by Arakoth's morphology, has broader implications. It suggests that the planetesimals, the small building blocks from which planets formed, were assembled not primarily through chaotic high-speed collisions, as had long been assumed, but through gentler processes of local gravitational collapse in which cloud fragments formed pairs and then slowly coalesced. This reframes the story of how planets grow from the ground up, and it provides some of the best direct physical evidence that early solar system formation was in some ways a quieter, more orderly process than the image of perpetual bombardment implied. Most stars in binary systems orbit each other on roughly circular paths. Gravity tends to circularize orbits over time through tidal dissipation of energy. But some binary pairs maintain highly elliptical orbits, swooping close to each other at periastron, the closest point in their orbit, and then retreating to much greater distances at apastron. These are called eccentric binaries, and when the eccentricity is high enough, the gravitational interaction at closest approach becomes intense enough to do something remarkable. It physically distorts the shape of each star. When massive objects come close to each other, their gravity raises tides on their surfaces, the same way the moon raises ocean tides on Earth, but far more extreme. During a close approach between two stars in a highly eccentric orbit, these tidal forces stretch each star into an egg shape, and then release it as the pair separates again. The star oscillates. It rings like a bell, struck by a passing fist, vibrating at frequencies set by its own physical properties. These oscillations produce a characteristic brightening and then dimming as the distorted star's projected surface area changes and its photosphere responds to the temporary energy input. Because the entire cycle repeats each time the pair sweeps through periastron, the brightness variations follow the orbital period with extraordinary regularity. On a graph of brightness over time, these systems produce a characteristic spike, a sharp, sudden brightening, followed by the rapid oscillations of the stellar body, and then a return to baseline until the next close approach. The shape of the light curve resembles a heartbeat on an electrocardiogram, and the systems are now commonly called heartbeat stars. The first well-documented example, KOI 54, was identified in Kepler data in 2011. It is a system of two A-type stars, about 2,600 light-years away in the constellation Cygnus, orbiting each other on an ellipse with an eccentricity of about 0.83, meaning at closest approach the two stars are much less than half the distance they reach at their farthest. The orbital period is 41.8 days. At each periastron, the tidal forces are strong enough to produce oscillations in both stellar bodies at exact integer multiples of the orbital frequency. The 90th and 91st harmonics of the orbital frequency turned out to be the dominant modes in KOI 54, a property that could be predicted from the known resonance structure of stellar oscillations under tidal forcing. Since the discovery of KOI 54, hundreds of heartbeat stars have been found in Kepler and TESS data. They span a wide range of stellar types, orbital periods, and eccentricities. Some show only the periastron brightening. Others show complex patterns of oscillation between close approaches. A few have been found to have tertiary companions, third bodies in the system whose gravitational influence perturbs the inner binary's orbit in ways that produce additional modulations in the light curve. The scientific value of heartbeat stars extends beyond their novelty because the tidal oscillations they produce are precisely tied to the orbital dynamics. Measuring those oscillations provides a remarkably direct window into stellar interiors. The modes of oscillation that a star supports depend on its density profile, internal composition, and rotation, the same quantities that are difficult to measure by any other means for stars too far to be resolved. Heartbeat stars thus function as naturally occurring seismographs, ringing at frequencies that carry information about their internal structure. Each close approach is a controlled experiment, repeated on a timer, in which tidal forces probe the star's interior and the response is recorded in the light curve. The phenomenon also illuminates the timescales of tidal evolution. Over many orbits, tidal dissipation gradually removes energy from the eccentric orbit, tending to circularize it. By studying heartbeat stars at different stages of this process, some extremely eccentric, some moderately so, astronomers can observe stellar tidal mechanics in action and test theoretical models of how binary systems evolve over millions and billions of years. The result is that a class of objects initially noticed, because their light curves look like heartbeats, has turned into one of the most productive laboratory settings in stellar astrophysics. In March 2018, a galaxy called 1ES1927+654 underwent a change that had never been observed before and for which no existing model had a ready explanation. The galaxy, located about 236 million light-years away, contains an active galactic nucleus, a supermassive black hole at its center that is actively feeding on surrounding material and radiating at high luminosity across multiple wavelengths. Active galactic nuclei of this type, called Seyfert galaxies, are among the most studied objects in extragalactic astronomy, with behaviors that are relatively well characterized. What happened to 1ES1927 plus 654 was not well characterized by anything. Over the course of about a year, the optical brightness of the galaxy's nucleus increased by a factor of roughly 100, one of the largest and fastest optical rises ever recorded for an active galactic nucleus. That alone was unusual enough to attract attention. But what happened to the X-ray emission during the same period was genuinely unprecedented. The coronal X-ray emission, the extremely energetic radiation produced by the hot, magnetized plasma that forms above and below an accreting black hole in a structure called the corona, nearly vanished completely. The X-ray luminosity dropped by a factor of more than 100 in the space of months, and the corona appeared to essentially disappear. This was a problem. In the standard model of active galactic nuclei, the corona is produced by the magnetic fields threading the accretion disk, the swirling disk of gas and dust feeding the black hole. Those magnetic fields are generated and sustained by the dynamics of the disk itself, and they are the primary mechanism by which energy is extracted from the infalling material and radiated as high energy emission. If the corona disappears, it means the magnetic fields in the inner disk have somehow collapsed or been destroyed. And without those magnetic fields, the disk itself, which depends on magnetic turbulence for the friction that allows gas to spiral inward, should also stop functioning efficiently. The proposed explanation that attracted the most attention was an extreme and rapid change in the magnetic field configuration of the disk, a field reversal in which the large-scale magnetic field that normally threads the accretion disk spontaneously flipped orientation. Such a flip, in theoretical models, would cause large-scale field cancellation, opposing magnetic fields meeting and annihilating each other through magnetic reconnection, which would temporarily destroy the corona and dramatically alter the disk's emission properties. As the new field orientation became established and the disk reorganized itself around the new configuration, the corona would eventually rebuild and the X-ray emission would recover. And that is, in fact, what happened. Over the following months, after the dramatic optical brightening and X-ray disappearance, the corona began to rebuild. By about 2020, the X-ray emission had recovered substantially, and the system appeared to be returning to something closer to its pre-event state. The entire episode, from the initial brightening to the coronal disappearance to the recovery, played out over roughly 2 to 3 years, which is extremely fast by the standards of processes involving supermassive black holes that typically evolve on much longer timescales. The detection of this event established several things that had previously been theoretical. Magnetic field reversals in accretion disks had been predicted by magnetohydrodynamic simulations, but observing one in real time was unprecedented. The speed of the process was faster than many models predicted. The detailed X-ray spectral evolution during the recovery provided direct observational evidence for how the corona rebuilds, information that cannot be obtained from any other type of observation. And the fact that it was detected at all was largely a consequence of the continuous, wide-field sky monitoring programs that have proliferated in the era of modern time-domain astronomy. Surveys designed specifically to catch transient and variable events that would have been missed by the pointed single-target observations of earlier decades. The event also raised questions about how common magnetic field reversals are in active galactic nuclei. If they happen regularly in the long lifetimes of actively feeding black holes, they could be responsible for some fraction of the variability that has been observed in active galactic nuclei for decades without a clear physical explanation. Whether one ES1927 plus 654's 2018 event was a rare extreme case or a glimpse at a common but usually less dramatic process is one of the questions that follow-up observations of this and similar objects are now attempting to answer. Every planet in the solar system orbits the sun. The sun's gravity holds them in place, defines their paths, and gives them the context in which they exist. This relationship between a planet and its star seems so fundamental that the word planet historically implied it. A planet was, by definition, something that orbited a star. But the universe is not bound by human definitions. Objects of planetary mass exist throughout the galaxy without any stellar host. They drift through interstellar space on their own trajectories, warming from no sun, illuminated only by the faint glow of distant stars and the cosmic microwave background. They are called rogue planets, free-floating planets, or interstellar planets, and their existence was suspected for years before the first confirmed detections were made. Some rogue planets likely formed as planets normally do, in the disk of gas and dust surrounding a young star, and were then ejected by gravitational interactions with other planets in the system or with passing stars. Giant planets forming in a protoplanetary disk can undergo orbital instabilities that scatter them to extreme orbits and eventually eject them entirely, sending them into the interstellar void. Simulations of planetary system formation suggest that this is a common occurrence. A typical planetary system may eject several planets for every one that survives on a stable orbit. If so, the galaxy contains more free-floating planets than it contains stars, which are estimated to number around 200 to 400 billion in the Milky Way. Others may form not as planets that were ejected, but as substellar objects that condense directly from gas clouds too small to trigger fusion. Essentially failed stars or isolated brown dwarfs at the low end of the mass spectrum. The line between a very low-mass rogue planet and a very low-mass substellar object is not always clear, and distinguishing between the two formation histories for a given detected object is difficult. The detection of rogue planets is challenging precisely because they emit no light of their own and orbit no star that might reveal them through transit or radial velocity measurements. The primary methods are gravitational microlensing, in which a rogue planet happens to pass between a background star and Earth, magnifying the star's light through gravitational lensing in a brief, characteristic event, and direct infrared imaging, which works only for relatively young, warm objects that still retain heat from formation. The OGLE survey and other microlensing programs have identified dozens of planetary mass microlensing events consistent with free-floating objects. The Roman Space Telescope, planned for launch in the mid-2020s, was expected to conduct the most sensitive microlensing survey ever undertaken, with the sensitivity to detect rogue planets down to the mass of Mars. One of the most intriguing detections came from the James Webb Space Telescope's observations of the Orion Nebula in 2023. Webb identified approximately 540 candidate free-floating objects in the nebula, young, warm enough to be detectable in infrared, with masses ranging from those typical of gas giant planets up to brown dwarfs. About 540 of them appeared to be bound in pairs, two planetary mass objects orbiting each other without any stellar host. These were dubbed Jupiter mass binary objects, or jumbos. Their existence challenged both the planetary ejection model, because the gravitational interactions that eject planets almost never produce ejected pairs, and the substellar formation model, because gas clouds as small as a few Jupiter masses are not expected to collapse efficiently. Whether jumbos represent a previously unrecognized formation pathway, or a failure of current models to account for some process in dense, star-forming regions, is not yet understood. Space exploration began with a question that seemed almost modest in scope. What is out there? The answers have accumulated for decades now, filling journals and databases and archives with observations of unimaginable variety. And what the accumulated answers reveal, more consistently than almost any other lesson, is that every genuinely good answer generates a better question. The universe keeps its strangeness available for anyone patient enough to look. If the questions explored in this video are the kind that keep you thinking long after you've closed the tab, the ones that sit quietly in the background and refuse to resolve, then this channel is where you'll find more of them. Subscribing means the next time something genuinely strange turns up in the sky, it will turn up in your feed